imagine you are driving a modern electric car, and what you don't see is a network of ECUs in that car that makes your ride smooth. Now let's focus on two type of ECUs which are there particularly in these all of the modern electric cars: ADAS ECU and the powertrain ECU. Let's focus on ADAS ECU, which handles the sensing and decision making, and the powertrain ECU, which manages the motor control and the braking. Now, these two ECUs at a real time when the car is driving exchanges lots of data like that of radar or the surroundings information detected by the ADAS ECU, and that data is sent it to the powertrain ECU for the speed control and torque control and braking systems of the car. Now, that is where AES encryption algorithm comes to secure communication between these two nodes for this so that not any data can be leaked or attacked when these two issues are exchanging the important data information between them. And that is where AES encryption algorithm comes into the picture. But here is the catch: not same AES mode or the same type of AES encryption algorithm is used for all type of data secure communication. Depending upon the data size, depending upon the mode of data from which it is coming, and what is the use case of data, there are different use cases onto which AES mode will be used. Now let's delve into that. And first one is the AES CBC. Now imagine that ADAS ECU is logging the important sensor data like dot of LiDAR maps or the vehicle speed profiles into the internal flash storage or SD card, which can be used for the further forensic reports or the compliances. And that is where AES CBC encryption algorithm comes into the picture. It is perfect for structured and block aligned data that has to be stored somewhere in the device, and it needs to be read later on. And in the case of AES CBC mode, there is an extra parameter of initialization vector, which is just like a string of bytes, and which is used to chain with the input message, with the input of fixed block size of 16 bytes to get the different encrypted data, even for an identical input messages, as we are doing the secure logging of the use case. And AES CBC mode is simple and best to use for secure storage of the data that's need to be read on later on. Why not other modes of AES modes are used? Well, AES other modes like of CTR, GCM, OFB, and the CFB are used for authentication and streaming type of use cases for secure communication. And AES-XTS is also used for secure flash storage, but it is used for a storage of sector-based input message, not the linear-based secure storage. So basically, AES CBC mode is used in where we want to securely store the data, and that's need to be read later on, and where speed and latency is not a very big concern. Now, how to use the AES CBC mode from an embedded software point of view, as that is how we are going to use for our embedded products like of IoT, drones, ECUs, or any other. Now, so in our software, there are generally two APIs: AES CBC Encrypt and AES CBC Decrypt. In both of these APIs, we'll be needing to send some parameters. First of all, taking the AES CBC Encrypt, first thing that we'll be needing to send is a symmetric key that will be having a string of bytes of either 16, 24, or 32 bytes of array. Second is the initialization vector, which will also be a string of bytes of 16 bytes that will be used with an original message to get the different encrypted ciphertext of identical blocks. And then third is a plain text, that is the original message that we wants to protect or that we wants to securely store, and that needs to be read later on. And then fourth one is the output or an array to get the ciphertext where we'll be having our encrypted data store. And then fifth one is a padding scheme if we are having less or the more number of bytes to be encrypted or decrypted. And then in the same way, the AES Decrypt API, AES CBC Decrypt API will be used, in which we will be sending all these five parameters, same symmetric key, same initialization vector, same padding scheme. Just instead of the plain text, now we are going to send the cipher text that needs to be decrypted to get the original message. And instead of the output of a cipher text text in our encryption API, we'll be getting an output in a original message format, that is plain text. That is the decrypted data that we have got. Okay, and second one is the AES CTR mode, which is mainly used for the encryption or for the secure communication of large size data, which needs to be encrypted and decrypted without any latency. Consider a scenario: there is an ADAS ECU which is detecting the lane detection or the obstacles around the car using the radar and lidar or radar sensor, and this sensor data needs to be quickly communicated to the powertrain ECU so that the corresponding engine or the motor driver can take the actions. And this data needs to be securely encrypted or decrypted as well, so that not any person can get this sensor information and control the vehicle. And this is done using the AES CTR mode for a secure communication. And one more thing about AES-CTR is that it is very widely used with the automotive Ethernet networking protocol. In the case of automotive, when we need to transfer the large amount of data at a high speed between the ECUs or the subsystems of an automotive vehicle, automotive Ethernet is the most widely and the new emerging protocol that is being used nowadays. And in that case, AES-CTR becomes the prime encryption algorithm to have the networking between two embedded nodes or the ECUs over the Ethernet very securely and safely. Now, how does AES-CTR encryption algorithm works is AES-CTR mode introduced the concept of the counter variable, and AES-CTR mode transforms the AES algorithm from block cipher to the strafing cipher. And how does it work is, it first of all encrypts the counter variable and then XOR the original input message that we want to encrypt using on the encrypted data of counter variable, so that in this way each data gets encrypted independently without of any other data, and no waiting, no padding is required. All the real time parallelization is only happens. Why not other means of other modes of AES for high speed and large data for secure communication? Because first one, the CBC will add the delay, as CBC mode will only work on the fixed block size of 16 bytes. So let's say if we have a large data of 30 bytes or 40 bytes, so with the multiples of 16, it is gonna first of all fill the padding, and then only encryption and decryption is gonna happen, which will cause an unwanted delay for the real-time processing of the critical data. CFB and the OFB AES modes use the output of a previous ciphertext to encrypt the next block of data, and this again will gonna cause the more time, like more processing and more delay for the real-time data exchange between the two ECUs having the large data size, and that's why these two modes are also not used. And after these three modes comes the AES GCM mode, which is mainly used for the encryption plus authentication based use cases. As in this case, we are the both ADAS and the powertrain ECUs are only doing the secure communication. Authentication will be the prior step before it. So AES GCM mode also using over here will add on an only an extra delay and will not be suitable for real-time critical sensor data encryption and decryption. And AES-XTS mode doesn't apply over this use case, as it is mainly used for the secure storage-based use cases. And how to use the AES-CTR mode? Now let's dwell into it. From a software point of view, we are gonna have the APIs AES-CTR encrypt and the AES-CTR decrypt. And in this case, we are gonna send a couple of 3 to 4 parameters onto it. The first one is gonna be the key, the symmetric key that would be of either 16 bytes, 24 bytes, or 32 bytes, depending upon the AES key bit size that we want to have. And then comes the counter or the nonce value. In the over here, we sometimes call it as counter value or the nonce value. And third one is the AES-CFB mode, which is used for the small and the slow speed data. Picture this: there is a technician who is checking vehicle's health by connecting a tool to the powertrain ECU, and at the same time, the ADAS ECU is helping on the diagnostics of the powertrain ECU by sending some small updates like of whether camera sensor is working or not, and whether the sensors are well properly oriented or not. And these updates travel control over a simple connection like of CAN or UART or the simple wired connections. And these data is on small bytes, and also latency is not so of a big concern. But what if intruder tries to physically read this data? So here data communication between powertrain and ADAS ECU should be securely encrypted and decrypted, so that not any fake technician or not any fake auto service center can leak this data and correspondingly get the health of the vehicle. And here comes the AES CFB mode for a secure communication of small data, and the where speed is not so of big concern. So in short, one can say that the AES CFB mode is mainly used for the small data which doesn't have so much of high speed latency, and the data which is communicated over UART, CAN or such wired protocols. Over there, AES-CTR mode is preferable for encryption and decryption. Like in the case of diagnostics, it's a small data which comes at a byte by byte. So CTR modes encrypts and decrypts one byte at a time. Also, another great thing about AES-CFB mode that most of our legacy ECUs, which are either communicating over CAN or LIN, which are the two widely used automotive wired protocols, these are the legacy ECUs, and CFB mode very well fits on this, as it is a small data which AES CFB mode can very securely encrypt and decrypt with not so much of big latency, and also at a compromisable speed. And why not other AES modes for the secure communication of small and the slow speed data? CBC mode works on the principle of block size, so it is unwantedly gonna wait for the block for the padding, like padding has to be done, or it is gonna wait for the full 16 blocks of data before the encryption decryption happen. And generally the small data can be of 5 bytes, 6 bytes or 8 bytes, so it is gonna add on extra processing and the extra much add on delay. Coming to the AES CTR mode, the CTR mode works on the principle of secure counter synchronization. That is, both the ECUs, the ADAS and the powertrain ECUs, should be having the synchronized counter value incremented in them as the parallel processing or parallel encryption decryption is happening. And while in the case of diagnostic use cases, it might happen that a diagnostic session is breakdown because of some XYZ environmental conditions, and in that case both encryption decryption will be happening in an unsynchronized way. It's like trying to read a secret message where both sides need to turn the same number of pages in a book. If one loses their place, the whole thing stops and not making any sense. Then comes the GCM mode, as it is an overkill, as GSM mode adds the not only encryption but authentication pillar of a embedded security as well. And over here it's the authentication would be the prior step before the encryption, so here GSM will not be preferable to use. And same way via the AES-XTS mode, it is mainly used for the secure sector based storage and the logging of the data. Fourth one is the AES-OFB mode, which is mainly used for the use cases where we have to do the secure communication in the noisy environment. Instead, there is an ADAS ECU which is communicating, which is sending the sensor data wirelessly to some system or chatting with another car wirelessly. The wireless connection might be a bit noisy, and sometimes you just can't ask for the message again if it gets messed up. And that is where AES OFB mode comes into the picture. Think of it like a secret code that changes your messages bit by bit. If one bit gets messed up, then only that bits get impacted. Rest of the message and rest of the data encrypted will stay secure, and not the whole message will be get messed up. And that is why AES OFB mode comes in handy. It works like a stream cipher. That is, it creates a special key stream and mixes it with your data. If a bit gets flipped during transmission, only that bit is wrong, not the whole part. And why not other modes of AES encryption? The AES CBC and CFB spread the errors across multiple blocks if error is occurred on one block or in an initial blocks of the data. GCM modes detects the corruption and it drops the whole packet. That can lead to the whole packet loss during the secure communication sessions. CTR limits the error, but it needs the strong synchronization communication between the two nodes. And is as it's a wireless communication, so synchronization cannot be guaranteed in every use case. XTS is designed for encryption and decryption of a storage use cases in a sector based flashing, in a sector based storage. And that's why other modes of AES are not so favorable to do the securely encryption decryption in a noisy environment, as AES OFB mode makes ensure that even if some bits get flipped because of the wireless communication, the rest of the data stays intact and doesn't lose. So one is the AES GCM mode, Gallius counter mode, which is mainly used in the use cases where encryption plus authentication is required. Consider a use case that a data being sent is not only data but it's a command. Say an ADAS ECU detects a hazard and it commands the powertrain ECU to reduce the speed of the vehicle. Here encryption will not only work, here we also need to check that whether the dot command from which the ECU is coming, that ECU is genuine one and not a fake one. What if someone replaces the ADAS ECU with their fake one? In that case, it can lead to the fake commands being sent to the powertrain ECU and unwanted and un, un and un and non-controllable behavior of the vehicle. That's where AES GSM mode comes into the picture. It adds the encryption plus authentication using the CTR mode encryption and the GMAC based authentication. AES GSM mode is the golden standard for doing the encryption plus authentication in a very high speed or in a very quick communication use cases, like in this case of ADAS and powertrain exchanging the data for how the vehicle should behave in during the some hazards being detected. And why not other modes can be used of the AES? Because CBS and CTR doesn't provide the built-in authentication schemes, while the CFB and OFB can encrypt, but it can't verify the sender from which the data is, from which the command is being coming. And XTS again here doesn't suit very well, as it is mainly for the secure sector-based storage. And last, and the sixth one is the AES-XTS mode. It is designed for encrypting the large blocks of data which needs to be stored in the external flashes like of NAND or the NOR flash. Consider that there is a powertrain ECU and it needs to store the data of calibration maps, AI models, or the weighted powertrain e-sensor data and all these. Then these data needs to be securely stored into the flash or the memory or the flash devices of an ECU or a car for later on the analysis or the compliance testing. And one of the major issue while the storage of secure storage is that the data can be of identical, the same data can be stored in large memory chunks, and that data needs to be securely encrypted so that not any intruder can just get the pattern of the data and get them. And that is where XTS mode comes into the picture. It has two separate AES keys and it includes the sector number, that is the address at which the data is being stored. So it encrypts the data not on the basis of the data value but on the basis of the address at which the data is stored. And this tweaking ensures that even if two blocks of data are completely identical, but their encrypted data or the decrypted data would be different from each other. And it also protects from the cut and paste and the reallocation attacks that the attacker can make easily on the storage devices. And why not other modes of AES? As all of the other modes, CBC, OFB, GCM, or CTR, these are mainly for the stream or the block cipher, not from the perspective of securely storage or secure logging of the data. Guys, also in between, there is one announcement that we need to tell you that there is a full cryptographic courses that we at Gettobyte are developing at our edu.gettobyte.com, in which all the AES related in theory that we are and practical use cases that we are dwelling into these videos, we do them practically via the use of automotive microcontrollers using our kits of our electronics version 3 and autobot version 1. And all of these courses are totally hands-on with real-time software programming, debugging, and analyzing how the encryption decryption works at not only at the simulation basis but at the hardware level. So do check out these courses.